Okay, so hi guys, so let's see what happens now. So we take our guy and then we suppose we want to, oops, we want to throw the rock. Okay, so this is a very bad drawing. How do you throw the rock? Yes, I know how you throw the rock. You do this. Okay, so you have a rock in your hand, and then of course we are on planet Earth. So we put the ground, we remember the radius r, this is the distance y that we know because we know our height. So the initial condition is there. We need to put our mask on as usual because of oxygen. There is no oxygen, so there is no air, and there is a mass. Okay, now this is the initial condition. Not, I mean, yeah, it's an initial condition, but it's not the initial condition of our motion. Because what I want to do is to study what happens when the guy throws the ball with the rotation. So you just rotate the body and let the ball or the stone go. Okay? So this will happen. So there is a full rotation. There is a so we don't know what happens here. Okay, so we do know, but the dynamic is complicated, and there's lots of it's super complicated basically to properly understand the dynamic of a throw. But the assumption is that what happens whatever is happening here, it's imprinting some momentum, meaning m times v momentum. This is the buzzword for saying that we have a mass and we have a velocity. Initial velocity is different from zero. So if you remember when we had our slide or our free falling object, the initial velocity was zero, and there were no force. There was only the pull of gravity, so the motion was one dimensional. And even in this case here of the slide, even though it looked like in two dimension, actually was just moving on a line, which is the line in this direction here. Okay, so that was it. Now we have something different because we have initial condition which says that in this direction here, let's make it easy. We don't want to play too much with trigonometry here. So let's do a dumb throw. So we throw it not upwards but straight forward. Okay, so the velocity is only in x. So whatever, I don't know, 3 meters per second. I don't know, maybe more, 10 meters per second. I don't know. Maybe it's a crazy throw. Maybe you must be Hulk. I don't know. Let's say 10 meters per second. And Vy is equal to 0 because we in y we don't have any, we don't throw in that direction, so we only have one component. This is to simplify a little bit the math, but the concept is the same. Now what's the difference? Now as soon as we leave the object, so we let it go, oops, the arm is still there, we let it go, okay, we have still one force acting on the object, which is the force of gravity. That doesn't change. We remember that G is Gm times r squared. We can safely neglect the component. It should be r plus plus y square. But this is like 1 meter and this is thousands of kilometers, so it's completely fine to ignore that change in the gravitational constant. So we just neglect it. That's fine. So gravity is acting in this direction, so the force is easy. We have only force in y direction, which is mg, and in x direction the force is 0. Okay, these are the two things. But now it comes the trick, the difference between what we saw before and what we're seeing now. So Fy is MAY is equal to mg as before, so the mass drops. And then actually I will show a video in which the mass doesn't drop, and I will next time I will do a video where actually the mass does have an effect, and it will be, you will see why the mass at some point cannot cancel out, or at least it does have an effect. So in this case it's the same, so the acceleration on the y-axis is g, and the acceleration on the x-axis is 0. Now what do we do next? If you remember, we need to integrate over time between time 0 and time 1, okay, and this is gt1, okay, because the integral of g times 0 times 0 is 0, because we set the clock in such a way that when we start measuring, time is 0, so we don't mess up with the origin of time. So, and this is the integration of our acceleration in y, but this is exactly the velocity in y, which is gt1, okay, and then we integrate further and we get that the height at which the coordinate y is exactly gt squared divided by 2, because we integrate once more, okay. I did it last video, so I'm not doing, I will just show you again. If we do gt in dt, is g is a constant, so it goes out, and then we have t squared over 2, because the integral of t is t squared over 2, we know that. Okay, so we've got y, but what about x? So let's write y somewhere, because I want to show you what happens mathematically and also in real life, even though we are not considering spins, rotations, frictions, and things like that. So y is g t squared over 2. Now ax is equal to 0, but if we integrate, so it's still the acceleration in the beginning is 0, but when we do v of x, we know that v of x is different from 0. So when we integrate it, it is actually 10 meters per second. So when we integrate vx over time dt, vx is constant because there is no friction, so vx times t1, that's the x component of our motion. So if we were to draw the cartoon here, the object would fall with this time dependence and with this time dependence here. Okay, so as you can see, if we put them together, and actually yes, we should put the minus here, because the force is going downwards. And as you can see, this is a parabola, right? Because we have y of t is minus gt squared divided by 2, and then we divide it, and this is yt, and then divided, and then we need to divide it by vx. Okay, but basically this is a parabola, as you can see. Okay, there is the vx. We wouldn't need to change the variable here, but basically what I'm saying is that we can bunch all the constant, the velocity, the 2 and the g, in a constant called k, and the motion, as you can see here, in x is t, so it's t, if you like, and then in y is doing this. Okay, so it's a parabola, and this is okay, maybe this is it's not to scale. Maybe 10 meters per second would be a much bigger parabola. Maybe it would be something like this. I don't know how many meters, but oh yeah, we can find how many meters, right? Because we know y is one meter and a half, suppose. So we can do. So let's do it. Let's just do it for the sake of it. So maybe it's unrealistic, and I pick a crazy number that you need to be the Hulk or Cap America to throw that kind of ball or stone. But let's see if I can do it. So we know that y then g times 2 divided by g over square root is the time. Okay, this is the time. We need to find the time, right? That it takes to get to the ground. And this is, suppose that y is 1.5 meter. So now we put 1.5 times 2 is divided by 9.81, and this is over the square root, and this is the time in second, right? Because we have meter divided meter second square over square root, meter goes away, second square is second. So this is correct, it's time. Dimension analysis is done. 1.5 times 2 is 3, so it's so roughly we can approximate this. Let me do the math completely. It's 3 divided by 10, so 1.3333. So it's equal to the square root of 1 over, so how is that? 1 over, let's say 1 over 3, roughly. Okay, and this is the time. I don't know how, I don't know what's the square root of 3. We can calculate it. You can take whatever. I mean, it's just an approximation. This is the time. Now we have, and now we have to find x. So x is 10 meters per second times time, which is 1 over square root of t of 3. So 10 is roughly 3 times 3. Right? So if I put 3, maybe I did something wrong. Anyway, so this should be roughly 3 times 3, because the square root. No, that's a sec. This is the square root. Oh, no. That's why I got it wrong. Sorry, I was confusing. So 10 is the square root of 100. That's easy. Square root of 1 over 3. This is the velocity. So x is the square root of 100 divided by 3. So it's roughly the square root of 33, which is roughly the square root 6 times, so 6 times 6, roughly 5.5. I don't know, 5.5 meter. So it looks like it's not too crazy. Maybe it's not too crazy because I don't know, there may be some, I mean, I should double check them out, but I think it should be correct. So what I'm saying is that so you can approximate those things, but you find the time, and then with the time you put it back here, and then you find the space. So you know the time because that's fixed by the height. It's like a free falling object. There is no much time left because there is only one force acting, which is the pull of gravity. But the good thing that is not it's not just a straight line. It's a parabola, and it's not in one dimension, but it's in two dimensions because we have x and y. They are both competing to each other, and the trace in the sky, it's actually a parabola, downwards parabola. Okay, so I hope I convince you uh, on the at least how to approach this kind of easy problem. Of course, if you change the angle, that would be it's an interesting point. What's the angle, the best angle to throw the object in order to maximize the length at which you throw the ball? That's a bit more complicated, not too much, but maybe for another time. But what I want to say next time it's what happens to the mass when we remove some of the assumption. Maybe we will keep them oxygen mass, but will be in water. So we will see the effect of the fluid on the mass, and that's maybe interesting. Okay, hopefully you enjoyed it, and I will see you next time. Bye.